All right, welcome everyone. Today we have the third lecture on line integrals, and these concern 15.3 and 15.4. But just as a short announcement, next week I will not be teaching because I will be away. So what I'll do, first I thought I would be able to ask someone else to teach a little later than this class. But I just heard that you have an ethics class, so that maybe that's not a very good idea. So what I'll just do is that I'll pre-record it for that one time and then I'll put it on YouTube. I mean, that's not ideal, but I mean, I'm doing that right now anyway. So I'll do it exactly in the same way that I'm doing it right now. And then the week after, I'm just back and teach normally. All right. Okay. So today we're going to extend the idea of a normal integral. So if we write the integral from a to b of f of x dx, what we mean by that is that we have an axis, the x-axis here, and our domain of our function is between x equals a and x equals b. And f has some profile over here. So I've just drawn the graph of this function. And then by the integral, we just measure the area underneath this curve. Whoops, like that. And we can define that by doing these Riemann sums and then saying that this integral is the limit of that. Now, we also know how to do things like integrals over a spatial domain. So then I don't have a line as my domain, a straight line, but I have some, let's say, an area which is now bounded by, say, x between two values and y between two values, and I have some surface above that, and then I would like to find the volume underneath this, and this is what this surface integral is. Okay, so what we're going to do now is to consider first today, we're going to extend the first of these line integrals, where we just have a straight line to start with, but these can become curved lines. And then in the lecture for next week, we're going to do general surface integrals. So the picture for a line integral I can kind of do, for a surface integral I kind of can't. But the idea is that rather than having a straight line as my domain, I have a curved line. And above that, so this is my r of t, which I've parametrized in some way. So this is a line, let's say in R2 or R3, it actually doesn't really matter. And then above that, I have my density. And so this thing may curve around because the curve curves around. And then I would like to know this area. And so f of r of t is now a density on a curve. And I would like to integrate this density. For instance, if it's a mass density, then if I do the integral, I get the total mass. If it's a temperature density, I would get the total temperature. I'm not sure whether that means anything in this case, but and so this kind of integral is denoted by the integral over some curve, script c, which I've parameterized with r of t, f. So I do the integral over this curve, f ds. And these kinds of notations are always a bit weird because they don't seem to mean very much. And that is true. They are really only something by which you denote something. So this basically just means the integral of f along the curve c. It doesn't specify how you actually compute it. The only thing that we actually know how to compute are things that we start with. So these ones, these are things we can compute. And also these ones are things we can compute. Yeah. And essentially the only reason why we know how to do these things is because we can rewrite them in like multiple versions of those by first integrating of the first variable and then integrating of the second variable. So that is really the only flavor in the book that we have. So we're going to reduce all these funny notations of these integrals to things of this type, and then we're back on our feet and we know what to do. That's the only thing that we can do. Yeah.
Are there actually other methods?
No.
Okay, so this is the only way to do it.
Yes.
Nice.
But there are lots and lots of different types of integrals that mean different things in different contexts, and they can all be reduced in some way to these things. So, and actually these are just infinite sums. So if you want to actually compute them in real life, you make them into finite sums. So you're just adding things.
Okay.
Yeah. In one way or the other. Of course, you have to know what you're doing to do the right computation, but in the end, it's just adding things. So without much ado, the length, so the simplest kind of density that we would like to integrate is just the density 1. And by that, what I'm actually doing is just as if I have, let's say, this in between A and B, and I give this thing the value, the height 1, what I'm going to get is the length of the part from A to B, because that is the same as this area. Right? The length is B minus A, and the area is B minus A times 1. So that's the same thing. And so the length of this curve is nothing but integrating the density 1 over this curve. And I believe I already did that last time. When we're doing parameterizations, I actually did that in the first lecture. The length of C, which is denoted by this integral, and so the value 1 that I'm integrating over is absent from the notation. Well, what did we have to do? Well, we had to say my t variable goes from A to B, and C is parameterized by the parameterization R of t. And what I would like to do is just know how fast R is traversing, or how fast is t is traversing through the curve. So that is dr dt. So that's the velocity, sorry, to be precise, is the speed with which t traverses the curve. If I just go with arc length, by which the speed is just 1, then the amount of t that I have to traverse is exactly equal to the length of the curve. And so then I would get b minus a. But that's a very special parameterization. So now, the only thing that I haven't really done is, so here I've said that there's a density 1, and this density I can write down over here. And so it is not so surprising that if I want to do this for other densities, that the only thing that is going to change is that this 1 now becomes f. And the only thing that really is added is that rather than just integrating f, I have to also take into account that I am going to go through this curve, and I'm going to go through this curve with a certain speed. And this is what this absolute value dr dt signifies. So more generally, this line integral of f along this curve C is nothing but taking the density at some point r of t with my parameterization r, and taking into account the fact that I traverse this curve with possibly non-zero speed. And this thing is something that we're familiar with. This is just some function of t. And if you can find an antiderivative, you can find this integral. If you can't, well, then you can't. And very often you can't. But in tests, hopefully you can. So this is really notation. and this is computation. Since the thing on the left is something that does not depend on the parameterization, right? I just have a curve and I have some density and that's it. And so the thing on the right, which I do have a parameterization, it should not actually, the actual outcome of that computation should not depend on the parameterization that I've chosen. Because if it did, then I should have to worry because the thing on the left wasn't defined, or the idea that I have about it doesn't have anything to do with the parameterization. It just says I have a density and a curve. And so that should be something that is independent of how I actually go through the curve. Yes?
That will say a density function.
Mm.
The question that I will try to imagine what exactly that is, what that would be.
Well, if you think of a volume density, that is, let's say, the number of particles, let's say if it's concentration, that's a density. Yeah, it's per unit volume. So what F is it measures something per unit of length along the curve. And so the total amount along the curve is the total amount per unit length times the bit of length, and then you sum those. And that is exactly why you have an F and a ds. So the ds is the length element. F has as a unit 1 over length, or something over length. And so if you integrate that, the length falls out and you get the total amount back. So that's why F must be some kind of density, a concentration, or per unit of length entity, which I generally call a density. But normally, if you want to be more precise, you call something per unit volume a concentration, and per unit area a density, and per unit length, I don't know whether there is a specific word for that. Yes?
Okay, this might be a stupid question, but can it then also be like a flow field?
We will come to that in the next
Okay.
thing. The answer is yes, but you have to worry about the direction of the flow field with respect to the curve.
Yeah.
In the sense that if it flows along the curve, you're going to get a different answer than if the flow field is orthogonal to the curve. We'll come to that in the next hour. So what I'm saying, what I mean by density is something that is not an absolute quantity, but that it becomes one after integration over some domain. I still call it a density. Okay, and so, but then the units will be different. Yeah. So this computation F ds should not depend, and it does not depend on the parameterization that I've chosen. And if you think about it a little bit, I mean, I don't want to go through a proof of that or anything, but if you want to do, if you do have a funny integral and you say, well, I want to do a substitution where I say u is 2x, and now I'm going to write things with respect to u rather than with respect to x, right? That's just the standard kind of techniques that you use to solve certain integrals. That is actually reparametrizing the curve. If you do u equals 2x, then you're shrinking the domain because u goes only between, let's say, 0 and 1, where x was going to between 0 and 2. So that is going through the same thing twice as fast. And of course, it shouldn't matter. You should be able to do the substitution, and it shouldn't actually make a difference in the answer. So that is the same here. So, so that's a good thing. So if I just do a little example of that, and I would like to know a curve. So whoop, this I is the thing that I want to integrate. So I is the integral over some curve, and I have x squared plus y squared. This is the function that I would like to integrate over some curve. And so if I don't specify the curve, this is meaningless. So C is the straight line from 0, 0 to 2, 1. All right, so that's this curve. The origin, 2, 1, that's the curve. X varies like that. y is in this direction. This is my curve, C. And I have to parameterize it by some scalar quantity, which I will always denote by t. So it makes sense to walk from 0, 0 to 2.1, so 2, 1. I could also walk in the other direction. But let's walk in this direction. And so then if t is 0, it should correspond to 0, 0. And if t is, let's say, 1, I should go to the point 2, 1. I could choose something different, but this seems reasonable to do. So how should the x variable change with t? Well, x should just be 2 times t, because then I go from 0 to 2. And y should just be t itself, because it goes from 0 to 1 at the same time. And this is a straight line. So the parameterization r of t that I choose is 2t times I for the x part and t times j for the y part. Now I have my parameterization ready, and I have to compute, to do this integral, I have to compute dr dt, the speed of this curve, which may be t dependent. In this case, probably not, because I'm going through a straight line. So I have to compute dr dt, and that is the square root of dx dt squared plus dy dt squared. Right, or x, so this is x times I, x of t times I, plus y of t times I, j. Yeah, and x of t and y of t are 2t and t respectively. So dx dt is just 2, and the square is 4, and dy dt is 1, and so its square is 1. And so this becomes the square root of 5. Per unit of t that I traverse, I have a length of square root 5. And that's the speed with which I go through this curve. Right? Square root of 5 lengths per unit of t. So I is the integral from 0 to 1 of f of r of t times dr dt times dt, sorry. And that equals, so now I just have to do what f of r of t is. And f was x squared plus y squared. But now I have to fill out what x is at a certain value of t. And so I have to substitute x equals 2t and y equals t in the definition of f. Arbitrary. Because I think that's a simple thing to work with. If you like minus pi to pi, you can do that, but you'd have to work harder to write down the parameterization. Yeah? So this is the integral from where here, I have now 2t squared plus t squared times square root 5 dt. And so from here on, I think you can work it out. So I should write brackets like that. Otherwise, the square root 5 is not multiplying the right things. And so this is 5 square root 5 times 0, 1 of t squared. I had 5 of these t squareds. And so I get some value. So let me give a small example where indeed I choose 2 different parameterizations and I show you that the answer doesn't change. So the example I'm going to take is this curve, a half circle, and I would like to find this integral y ds over this curve. And so this is also the moment of c about y equals 0. So I don't particularly care about those interpretations. We're doing calculus, not classical mechanics. So let me say, let me first choose this parameterization 1 of this curve. Well, I actually would like it to go from the point a, 0 to minus a, 0. So it's not a standard circle, but it's one that is at the size, or sort of a radius a. So it makes sense to do this in cosines and sines, and say r of t is a times cosine t times I plus b, no, a times sine of t times j. It's a standard parameterization of a circle, and t then runs between 0 and pi, a half circle. Right? Well, then I have to compute the speed of this curve, dr dt. So that's the square root of a times the, sorry, a squared times dx dt. So that is minus sine of t squared times a squared. So that is sine squared of t. And the derivative of a sine t with respect to t is a cosine t. So if I square that, I get a squared cosine squared t. And I, of course, use that sine squared plus cosine squared is 1. And so I just get the square root of a squared, which is a. In other words, I've chosen a parameterization where, because in a standard circle, the cosine t sine t parameterization has arc length parameterization, and now it goes slightly faster because the circle is bigger if a is larger than 1. And so I traverse with unit, if I take a unit of t from 0 to 1, I have traversed length a along this circle. So the speed is a, meters per unit of t, so to speak. So this is not surprising that this speed should be a. All right, so then we have our integral y ds, and y is now a times sine of t, because that is the parameterization that I've chosen. And t went from 0 to pi, and the speed, dr dt, is a. And then I have dt. So I have a squared, and then I have the integrals of sine of t between 0 and pi. So this becomes minus a squared cosine t between pi and 0. And this is 2a squared. Some number. Let me take a different parameterization, namely one in which x goes from a to minus a, and y varies between 0 all the way to the top of this thing back to 0. And so r of t I'm going to take as, I'm actually doing it with x now because I have essentially x as my parameter. So it's x times I, and I have a squared minus x squared for the y variable, because this is a circle, times j. Go ahead.
So in the last example, 2a squared is the density.
It's not so much the density of the curve, it is the density of y along the curve. I can easily skip the word density in whatever I do. It doesn't really matter. I'm just integrating a function along a curve. And often it is interpretable as a density, but I can just mean it doesn't really matter. Yeah, so if I take x as my variable, it goes from minus a to a, and y varies as square root a squared minus x squared. This looks worse than the other one because at least I think so. So now I have to do the dr. In this case, my independent variable here I've taken to be x, because the x coordinate I'm going to take as my time variable. And so dr dx is, well, it's 1 times I, because dx, the derivative with respect to x of x is 1. And the derivative of y, which is the square root of a squared minus x squared, with respect to x, is x over this thing. And I have to take the square root of these different quantities and sum them and take the square root. If you do that, you get the square root of 1 plus x squared over x a squared minus x squared, which is a over a squared minus x squared. But the speed with which you traverse this curve is really different from the previous one, because at the beginning I traverse it very fast with a little bit of change in x, but somewhere in the middle I actually traverse it rather slowly in this parameterization. So now I have the ingredients, and I just hope that I don't get stuck in doing my integral. So this is the integral now. X goes from minus a to a. Y was equal to a squared minus x squared. And then I have the speed with which I traverse the curve, which I have computed. And you see that you get lucky. Well, not entirely. That the thing that you wanted to integrate also becomes the thing in the denominator, and they cancel. So the hard parts fall out. And so this is a times minus a dx, and this becomes 2a squared. And this is the same number as before. So the parameterization didn't matter. So your task really is choose a parameterization that works easily. Writing down a parameterization is often not given, and you have to work on writing those, finding one for a curve, and then work with them and make it your life simple. Let me do a little more involved example. This is example 4. And here I have to paint a pretty picture. So I have this paraboloid in 3D, z equals 2 minus x squared minus y squared. And in the first octant. And I also have in a different color this kind of curve. And so this is z equals x squared. And so x is along this axis, y is along that axis, and z is along the vertical axis. And so this parabola z equals x squared is just a parabola in the z-axis, z and x axis. But now I make copies of those in the y variable, in the y-axis, because this thing does not depend on y. And so it's a surface. And I'm looking at the intersection between these two surfaces. And this, of course, is a little hard to draw. But it's a curve that kind of goes from here to there. It's the one that was colorblind last time. Well, he's also he might be watching. But it's a curve that is sort of over here. And so this is the intersection curve. And this is my curve. And I would like to find the integral of xy over this curve. Well, this is a hard problem. For one, because we do not have a simple description of this curve. The only thing we know is that it lies on the intersection between the curves. And so we have to do a little bit more work. And it kind of makes sense to say, well, this green surface, the parabola, this parabolic cylinder, so to speak, in green, has the simplest prescription. So if I take t to be x or x to be t, then the z variable should definitely be equal to the square of that. Because otherwise, this curve doesn't lie on this green cylinder. Z being x squared. All right, so, and that's fine. And then, so the only thing I haven't actually specified is y, but y I could get from the other parabola, the paraboloid, the orange one. So on this, or it's an ellipsoid actually. So for that, there should be a 2y squared. Sorry. 2y squared. So for on the parabola, this ellipsoid, I have 2y squared equals 2 minus x squared minus z. Simply because the point x, y, z has to be on this surface. And so 2y squared has to be equal to 2 minus t squared minus t squared. So that's just 2. And that should be 2 minus t2, sorry, 2t squared. Sometimes when you're sitting and doing these computations, you can't see the wood for the trees. So y squared is just 1 minus t squared. For a moment, I thought that my t squares were just gone, and I thought that can't be right. You know the joke of this number theory professor who wrote down 7 times 9 is 67. He said, well, that's not right. It's 63. And then the professor said, no, it's either, no, he said it's 61. I said, well, it's either 61 or 67. It can't be both. Anyway, so y is now plus or minus the square root of 1 minus t squared. And we have to check which one of the two we have to take. And so 1 minus t squared, t goes from 0 to 1. This point you can check is x is 0. And this is 1, 0. And the other point has x being, x equals 1, y equals a half. I have to now have a look for a moment. Do I care? I actually only care about the x coordinates. So here my x is equal to 1, equal to 0, and here my x is equal to 1. So since I'm parameterizing the curve by the x coordinate, I have to worry about that x goes from 0 to 1, and x equals t, so t goes from 0 to 1, and y is positive on this range, because my curve lies in the first octant. And so I have to take the plus square root. Otherwise I would have parameterized it at the sort of below 0. Yes. Yeah. I just want, so you have to know where t lies, and to know where t lies, you have to look what x does. And that's why I went back to the picture. Yeah. Because t might have run from, well, in this case, I want to take a square root of something anyway, so it has to be positive. Right. I didn't have to do this. Yeah, you're right. All right. So now I have my parameterization ready. T square root of 1 minus t squared and t squared. And so r of t, just to be specific, is t times I plus the square root of 1 minus t squared times j plus t squared times k. That's my parameterization. And I have to compute the RDT. And take the length of that vector. And so that's going to give me the length of I. And the second is the derivative of the second with respect to t. So that's this thing times 2t with the chain rule times j and 2t, the derivative of t squared times k. Square all of these and sum them. So that gives me the square root of 1 plus, if you work that out, t squared over 1 minus t squared and 4t squared. And that apparently is 1 plus 4t squared minus 4t squared divided by 1 minus t squared. This looks horrible. But you do notice that the square root of 1 minus t squared is in the denominator. And y is in the integrand, xy. We have to integrate x times y, and y equals the square root of 1 minus t squared. So those are going to cancel.
4t squared as well.
No, it's 4t to the 4th, sorry. But you're right, otherwise they would also cancel. Yeah. All right, so this curve x, y, ds, that's the task in front of us, is the integral where t runs from 0 to 1 of x, which is equal to t, times y, which is 1 minus t squared, times the speed. And we just computed that 1 plus 4t squared minus 4t cubed to the 4th divided by the square root of 1 minus t squared. So just underlining those two, they cancel. I don't want to write through it. So we get this thing. Still looks pretty bad, but now we're in the realm of standard integration techniques, which of course you do not know by heart anymore, but we will practice them again in these lectures. So how to do this one? This is actually not an easy one at all. So let's say that we take u equals t squared. We have t squared and t to the 4th. So that's just one thing and the square of that thing. So it makes sense to take u equals t squared. And the bonus of doing this in this substitution is that the derivative du dt, which we have to take into account in our substitution, is 2 times t. And that is essentially the factor that is in front. So this makes sense, especially if you've done it a couple of times. So du equals 2t dt. And so writing everything in terms of u gives me 1/2 du. That's the t dt. And then 1 plus 4 times u. Let me write that with different letters. Minus 4 times u squared. And I have to worry where u goes from where to where. If t goes from 0 to 1, well, the square of 0 is 0, and the square of 1 is 1. And so this integral is still an integral from 0 to 1. All things you have to worry about. This is still not a very easy integral. So I'm just going to do that. You have to do what's it called? Splitting of the square. Not something you do every day. So if you think I really have no idea how to do this, practice it again. This is how you do that. Oh, yeah, one of those things, yeah. And so this now gives us a new substitution, where now I say v equals 2u minus 1, and dv equals 2 du. Yeah, this is a horrid one. And so I get another factor of a half. And v goes from -1 to 1, where u goes from 0 to 1. But I have 2 minus v squared dv. This is as simple as it's going to get. Yes.
Why is it 1/4?
Because of the 2, the value 2 here. Yeah, so here I have to replace du by dv. And so du equals a half dv, and that is a half that is in this factor of a quarter. So either you know your standard integrals, and I do not know this one by heart, or you say, this is actually nothing but the area of a circle. Why? Well, because let me think. I now had a nice picture in front of me. And okay, let me see if I can explain this to you, because this actually is not in the book. So the picture I want to show you is this picture, where here I have square root 2, and here I have minus square root 2. And I am traversing v goes essentially from -1 over here along this circle to +1, which is over there. And so the integral that I'm computing is twice this area. It took me about 10 minutes to figure out the right way of thinking about this. And so this is 1/8 of a circle of radius square root 2. And so now that's this bit. I should have thought about this just a little longer. So v is along this axis, and it goes from here. So let me think about this for a moment, guys. I'm going to stop the recording now because I know that I'm going to have to explain this bit, but I'm coming up with the explanation while I'm doing it, and that is not beneficial to the talk. So let me think about this for 3 seconds, and then we'll come back to that after the break. You can also do it by standard integrals by looking at the back of your book. It's all a bit here and there, but you get something out. But let me explain it after the break, so I can give you a proper explanation.